Last time we talked about, general relativity and before about the properties of space, or we could also say, what if the universe is an elastic continuum of some kind of substrate that has elastic properties? And we saw that we can explain general relativity as refraction. So now today we'll talk about special relativity. So for instance, why do all observers locally see the same speed of light? Why do moving clocks run more slowly? And why is there length
Now,
contraction?
real quick, I just want to. Why do all observers measure the same two-way speed of light?
Yes, we will
It's
actually
very
also talk about
important.
the one-way speed, but you're right. So far,
Well,
I
but
think,
but no one observed. I mean, the one-way speed has never been observed.
yes,
Special
correct.
relativity, yeah, special relativity presumes that the one-way speed of light is the same as the two-way speed,
Which
and
sounds
that it's
pretty
the same for
crazy,
all.
right? Yeah, yeah. But I have a
Yeah.
demo on that too. You'll see.
Okay.
We'll try to trick the system. So basically,
It's
we'll
I
try to
just
trick
want
it.
like I want to put that as a I want to put that as something that just always need to be clarified and shouted from the mountaintops, which is
Yeah,
that
you're
like we
right.
don't know the one-way speed of light,
That's
even
true.
though
Yep.
special
Mhm.
relativity presumes that we do,
Yes,
basically. And
exactly.
that is
Yes.
just a convention. That's not an actual known fact. Anyway.
True. Yeah. Good point. Good point. Okay, now before we start, I was watching your episode with the Mystify Psi, and so I
Mhm.
thought it might be a good idea to actually start to write down, what are our assumptions, what are the premises, what are the hypotheses, which are the derivations to make sure, first of all, we are really clear in our heads what are the assumptions, and also later that we can see if anything goes wrong anywhere, right? That we can go back to see, well, what was the assumption it was based on, or what was the derivation, the deduction? Was there a mistake? So, and I'm going to keep adding to this over time, and then maybe you can maybe help me fix anything because this is not my area of expertise, but I thought it might be helpful as an exercise also. Um, so far, what we have assumed is, the hypothesis is that there's some kind of elastic continuum and it's deformable. So this continuum, whatever it is, we call it either ether or substrate or medium, it fills all of the observable universe. And one important thing is that we think it supports shear waves, transfer waves. And that means that, it supports Hooke's law, linear elastic response, basically, at least for small strains. I'm not making any claims or any hypothesis yet about large strains, but at least, in the small strain area, it's elastic. Um, Also, another hypothesis is that everything in that universe is a kind of an excitation of this continuum. So basically, a wave, it could be a standing wave or a moving wave or some kind of deformation. And that includes anything, fields, lights, light, charge, matter. And of course, this will talk a lot more about in the next episode to see what's the justification for that. Like, why would we be so crazy to think that matter is waves, right? There must be some reason we think that. And so this will be in the next episode. And the third one, we won't
Uh,
need to. Yes, go ahead.
but go ahead and finish your point. I wanted to ask a few questions before we go to H3.
Oh, go ahead. Yeah, go ahead.
Okay, so now when we say deformable, we mean alterable in some internal property. We don't necessarily mean that the parts get displaced from their resting position, right?
Yeah, I would call it elasticity. Well, elasticity is defined. I actually have the definition right here in front of me.
Okay.
Elasticity means the ability to deform of a deformed material body to return to its original shape and size when the forces causing the deformation are removed. So actually, I have a little demo here. Just it's just really simple on the Hooke's law. And maybe you can tell me now if you can see if the frame rate is okay for you now, or is it still like really
It
awful
looks
choppy?
great
Oh,
to
it's
me. Yeah,
better.
it looks great.
Good, 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 good. Yeah. So basically, all we're saying is basically it's basically Hooke's law, right? So there's some restoring force F, and it depends on some constant. How stiff the feather, the spring is, and
Hmm.
the displacement. Of course, displacement could be anything, but when I do the simulations, I usually mean actual displacement. So in some spatial direction, that's what I mean. Now, I don't know what it means in terms of the detail, down at the detail level, what happens, but there's some kind of displacement going on in a spatial dimension. And now in the ideal elastic solid, okay, if it's perfect, there's no damping, right? So if there's no damping, it means the wave will go on forever, right? This is when there's no damping at all.
Hmm.
This is basically if you were perfectly
Yeah.
linear, elastic. Now, the thing is, we know from light, right? It can travel for billions of light years and it's still not really, it's still there. So if there's damping, it has to be very small. So there could be a very, very small amount of damping. That's possible because there is redshift. So maybe we'll talk about that later, right? If this could be an explanation for redshift even, but it can't be damped very much, right? If you have a lot of damping, you can see the wave, it disappears after a while, right? It stops and we don't see that, right? So this is why it has to be at least, you know, it has to be, it can't be damped, but it has to be really, really a small amount of damping, if anything at all. And the third one was
Yeah.
just basically for last time, when we talked about general relativity, we said that waves, the wave energy, the stored wave energy in a volume can slightly alter the stiffness and density of that medium. And what that actually implies that there's some weak nonlinearity there, which is interesting also for later when we talk about other things. So yeah, and today we don't need this one today. Um, Another thing is, well, now we have these few hypotheses. What can we derive from that, right? Just from these very simple ones. And what we have done derived so far is basically what can we say something about the nature of that medium? And basically from these hypotheses, we can say, well, it's got to support transverse waves, right? So here's a small demo. This one shows just gas. So could it be a gas? Well, for gas, we know there's no there's no stiffness, right? So even if we have a transverse wave going on, it doesn't really go anywhere. We can have longitudinal waves, obviously, in a gas. That's fine, but not transverse, right? So what about
Mm.
liquids? Liquids are similar. So we can have longitudinal waves, but transverse,
Whoa, cool.
they might go for a little bit, but then stop, especially if there's absolutely no viscosity. If there's viscosity, now, if there's viscosity, we can actually get transverse waves. And I know there was a comment on the last 2 videos ago. So yeah, you can see these constituents, whatever, they start to, move in a transverse fashion, but it doesn't go very
Mm.
far, right? So if there is some kind of viscosity, it has to be super stiff because it has to explain light waves. It has to explain how come a light wave can go for billions of light years, right? Without damping. So it can be slightly viscous, but I don't know exactly how large that number would be, but at least it would have to be very small. So the only thing really, it has to be some kind of solid, and by solid mean an elastic solid means it can be when it's deformed when the external force is gone, it tries to go back to its original state. So a solid just means there's some stiffness here, right? So these constituents are somehow connected in an elastic fashion, and if it's very stiff, it will go very fast, and it will go also for a very long time, basically.
So it needs to be amenable to transverse waves
Yes.
because of the existence of, and we know that because of the existence of light,
Yeah, I mean, no,
right?
light is polarizable, right? We can polarize it. So we know it has to be transverse. It can't be a longitudinal wave. We know it's a
Hmm.
transverse wave because of the polarization.
Okay.
That's why, yeah.
Yeah.
Um, and from this, we can actually already derive really uh, basically. And then I want to spend too much time on this. I thought maybe we could have a separate episode on all these details because I have more. I also have the premises and all that stuff. But just to give a rough overview right now, um, based on just on that alone, we can derive that basically there is a transverse wave satisfies a wave equation with speed c, and we have talked about this already last time a little bit. And based on also on these two hypotheses, that means if everything is composed of a wave, of some kind of wave, that means also our clocks are made of waves, and our matter is composed of waves, and our rods are made of waves, which is important for our discussion today. And maybe I'll just mention the last one for special relativity. This is what we'll talk about today, right? So basically, from these hypotheses, on these definitions, we can then conclude that the wave equation is Lorentz invariant, that moving bound waves, so matter waves, show time dilation, length contraction, and relativistic Doppler effect. And this is what we talk about today, basically. What's
Now I have one more question.
Yeah,
In your hypothesis, all of the different phenomena are waves, basically, in this same elastic solid.
yeah, at least
Um,
so far.
so
Let's see how far we
so
get.
you
Maybe
know,
there will be a
Matt,
point where it doesn't work. We need something else, but well, I want to push it as far as possible until we hit a wall.
right? I shouldn't say all of the phenomena. I'm saying all of the major phenomena we have discovered so far
Yes, yeah, yeah, that's true.
can be
Yeah.
integrated under waves of the same one medium.
Yes, so far. Okay, I can add it so far.
Yeah.
Be
So all
really
physical
specific.
phenomena, yeah, so far. Which kind of goes without saying, by the way, but we want to be precise just in case someone gets confused on that point. Because obviously we're
Oh
not
yeah.
going to be unscientific and start making claims about phenomena we haven't
No,
yet
absolutely
experienced.
not.
Like
Yeah,
those
yeah.
are also made of waves.
Yes.
Well, we don't know that.
Exactly. We need to be
So
really exact. And I think this will probably need a lot of refinement, the
yeah.
wording and all that. And I started a document, so maybe I can share it with you also if you want to participate or something. We can,
Okay, yeah.
we can also have a graph where
But
we say it's a subset, right? This is just a small subset for this discussion. For instance, we observe that light is transverse, right? Polarization. Like we know that light and matter, they show interference patterns, which I will talk next time. So basically, this leads to our hypotheses, these two, which are not unreasonable because there's some evidence for that these make sense. And then based on that, we can build this whole graph. And then the good thing also is if there's anything wrong, let's say down the road, we see like, oh my God, induction, for instance, right? Oh, it doesn't work. Well, what led to that? Like, what definition did we have? And then maybe we made a mistake somewhere, or maybe there's something we have to add another hypothesis, or maybe we'll have to change one, right? So I think that way makes it easier to track also if there's any error, like does it break the whole thing, or is it just something that has to be rethought, that kind of thing. Also,
um
yes,
hang on. My question from earlier was, you're positing that these different phenomena are waves in the same medium.
yes.
Are they different kinds? Is each different phenomena a different kind of wave? Like, is a matter wave a certain kind of deformation, then a light wave a different kind of deformation? What
Okay.
what are the differences between the different kinds of waves?
Yeah, we'll talk a lot about this in the future episodes, but in
Okay.
principle, I would say very shortly that light is basically a traveling wave, a traveling transverse wave. And
Okay.
matter is some kind of, like for an electron, it's some kind of circular wave. Some people say it's like light going around the circle twice, for instance, in a
Hmm.
and they have simulations for that too. Now, because this is, of course, we'll have to dig deeper into these details, but basically, it explains also why light can be turned into matter, right? So, and also why when you have a positron and electron hit each other, right, they annihilate and they generate these gamma rays, which are just light waves. So that kind of makes sense that you have light can easily turn into matter that way. So light is matter is basically somehow curled up light wave, if you want to call it that, or you can also express it as a different wave function, right? There's different kind of wave functions. There's the transverse wave function, but there are more complicated ones too, right? Circular waves, all kind. I mean, there's so many different wave shapes, right? We can have. So I would say it's all the same, built on the same elastic medium, just different kind of waves in the medium.
Mm-hmm.
Yeah.
And finally, gravity would be a alteration in the optical density of the medium, which
Yes,
is what we
exactly.
talked about last time. And
Yes.
so I'm okay, so it's starting to come together. The
Hmm.
You're modeling light and matter as deformations in the medium,
Yes.
and then gravitation as the optical the possible alteration of optical density.
Yes.
Gravitational waves being a wave of optical density in the medium.
It's actually
Okay.
also a transverse wave. It's just slightly, it looks that the wave function looks a little bit different. So a normal, a simple light wave is just either up and down or circular polarized, right? And the gravitational wave that we saw last time is basically this. I don't have the simulation open right here, but it's kind of this. It's also a shear wave, but it looks like a circle that you flatten and then like two ellipses. You know what I mean? You saw the demo last time, right? It's also a
Yeah,
transverse wave, just a different kind. Yeah,
right.
basically. Yeah,
I see.
yeah. Now,
And all of these statements about the elastic medium, from the statement that it is an elastic medium to the statement about matter and light being transverse waves in the medium, all of these should be taken as analogies. We're not literally saying that the ether is made of a elastic solid, but rather that there's an analogy to the behavior of an elastic
oh, good
solid. Is
point.
that
So the
fair?
next slide will address this. So also all
Okay.
the things that we did not assume, because that's also important. So as an example, we did not assume the speed of light is constant for all observers. There's something that kind of emerges from this, right? We did not
Mhm.
assume that the geometry is fundamental either, because that also emerges from the propagation speed from the optical density, all that. And also and at least we did not assume anything about the microstructure of this continuum or even what this continuum is made of. You know what I mean? So I don't know. I couldn't answer that, right? It's what I would say it's not made of any atoms for sure, because that would be circular logic, right? Because atoms are made of waves. So I couldn't tell you what this is, right? Is it a substance? Is it, who knows, right? When there's something, the good thing though is that in terms of the explanation and the mathematics that comes out of it and the wave function, it doesn't make a difference in that sense. It makes a philosophical difference what it is. And maybe there will be in the future experiments that would, maybe there's some observations that would give us a clue if there's any difference. But whether, it's kind of continuous or is it some kind of a crystal structure, or is it a foam? Some people use diamond structures. I don't know. And so I don't think we should assume anything until there's a reason to make this assumption. So I want to basically make the fewest assumption possible. So I would say this elastic continuum is definitely real. I mean, it exists as a real thing, not mathematical. Okay. So in that sense, it is a real elastic, but I don't know what you mean with the word real. Of course, is a bit difficult to define. It's not mathematical. So there is something there. It is elastic, basically.
It really is there. It really is a medium,
Mhm.
but we're not literally saying it's a solid because you've said so yourself that matter is a wave in this medium.
Yes.
So it can't literally be a solid, but because solids themselves are waves in this medium.
Oh, that's what you
You're
mean.
saying
Oh, I
that,
get
yeah,
it. Yeah,
so it
yeah, yeah,
can't
yeah. Well,
literally
okay.
be a
Yes, yes.
solid. We've gone over this before, and it's worth going over like
No, I get it.
often because it's
Yes,
easy.
of course. That makes, yeah,
Otherwise,
yeah, yeah.
it kind of sounds like I mean, it's just an imprecision. We have to be
Yes, no, I agree. Yeah,
clear
yeah,
about
yeah.
this. And so I think of
Mhm.
when you say it's an elastic solid, you mean this analogously. Each part of it acts on the next part in a way that is analogous to the parts of an elastic
Yeah,
solid act
because
on one
it's
another.
not like basically when you look at the simulation I just did before about that gas, in the gas, the parts, there's no resistance, right? They just move. There's no stiffness. So it's not like in a gas. It's not like in a liquid. It looks more, if I had to visualize it, of course I visualize it, it looks more like a solid because the parts there are somehow the neighbors can pull on the other neighbors in some way, right? So that's what I mean with solid. The structure, the way it would look like if we had like in the future, if there was a way to look at it, maybe it would look more like a solid than it looks like a gas, right? Do you know what I mean?
Yes.
Yeah. It's just the way these parts are, is there any coherence to it? Is it totally frictionless, or is there some connection, right? Because the elasticity demands that if one neighbor pulls, the other neighbor kind of reacts to it in some way, right? That's what I mean with elastic solid. There's no elastic gas, right? There's no elastic liquid. If it's elastic, it's some kind of the structure looks more like a solid.
Right.
Yeah. Also, I didn't define whether, I don't know whether is it space itself or is it something in space? And then again, this is important for philosophical reasons. But right now for us, it wouldn't like special relativity wouldn't look different, right? If it's actually space or if it's something in space, we couldn't see the difference right now. Maybe in the future or also philosophical, there might be difference, right? But in terms of what the effect from that is, I don't think we have to decide or define that. We don't need to assume, I think, either way.
I agree that we can table this issue while talking about your theory, but I think it makes no physical sense to talk about this as space, deforming,
Mm.
because a deformation is a movement,
Yeah,
and
yeah, that's
movement
true. Yeah, yeah.
means a change in spatial relationship. So I think it physically and philosophically makes no sense to call it space.
How
I
about
continue to
vacuum? What word would you use? Would you say vacuum because the vacuum is in space, or is that the same?
I think vacuum should just be thrown out because I
Okay.
mean, well, vacuum should just mean an absence of matter. And it shouldn't
Yeah,
mean an utter emptiness because there is no such thing as an utter emptiness because nothing isn't a thing. So that violates one of the basic
right.
laws
Yeah,
of
yeah.
existence. So vacuum should be we should just retool what that word means to simply means an area of ether which doesn't have any matter in it.
Yeah,
Okay.
yeah. Okay.
Because
Hmm.
that's historically what that word has meant. Like I sucked the air out and now there's a vacuum. It doesn't mean there's nothing, it means there's no matter, an absence of matter. Then
Right.
space means relationships between entities. Okay.
Mm.
It just and then the medium or the ether or the plenum, that's the thing we're talking about today.
Yes, yes, exactly.
Yeah, that's how I conceptualize it, and I'm very open to discussing the ins and outs of that. I think it's important to conceptualize that properly.
Yeah, yeah, makes sense. So we've talked about Hooke's law briefly, and of course we've been talking about waves a lot. So I just wanted to show a brief demo of what waves, what is actually a transverse wave, just briefly. We often see these equations, and basically what it means that the acceleration is on one side, and we have the curvature on the other, and they influence each other, right? So more
Hmm.
acceleration means more curvature, and vice versa. And we here's just a small demo that also shows a bit the elasticity aspect to it. So if you have just this elastic band, for instance, with strings with beads, and you pull on one of them, right? When they are elastic, we can basically see that one point affects the neighboring point, right? And so when we
Hmm.
calculate, we can also automate this. When we calculate the wave, we can see that the neighbors. So when we calculate this, the middle point here depends on the displacement of the neighboring points, right? And I think you had a good video on this too. You had something similar where you were arguing, well, this is really an indication that there must be some kind of ether, because otherwise, how could one, point in space be affected by other neighboring points in space if there's nothing there? So this kind of illustrates this. Yeah, and we can make it
Yeah,
slower or faster. So you can play with this, and you can also see the calculation, what it means in terms of the acceleration that we get. So the more we pull it, right, the more acceleration you get. So
yeah.
just to get a feeling of
And
also the elasticity, right? There's something you need something elastic to be able to do that. If these beats, if there was no like nothing in between, like nothing would be happening, right? They wouldn't be affecting each other. So this requires some kind of elasticity, basically.
I see. And so what you were saying in the equation is curvature leads to the acceleration of any one of these units. And let's break that down. if there's a if there's a curvature to the relationship between the units, that means
Yes.
any one of the units is going to experience an acceleration.
Yes. Hmm.
Then once that acceleration happens, the curvature will change, which will then lead to some different acceleration in the
Hmm.
future. And all of
Yeah.
that is happening differently for each one of these units. And that is what gives us the beautiful pattern that your simulations illustrate for us.
Yeah, and it's pretty simple. It's all based just on elasticity. From that, you get to Hooke's law. From that, you get to the wave equation. And from that, we get to, let's say, look at this in 3 dimensions. So
Yeah.
I just love the visuals of this one. Okay, I hope you can see it better now, because last time the frame rate was so awful, but I think that just looks so cool.
Yeah, that is really
I
cool.
just love playing with this stuff. Anyway, so here we can
Hmm.
see now we have this whole thing in 3 dimensions. So we don't have just one spring. Of course, this is an analogy, right? Some kind of elasticity, I'm visualizing with a spring. And we can now hopefully try to understand that, once given that K constant from one spring, when we add it all up together in this, depending, of course, how it's constructed, right? There's an overall stiffness now to this. medium. And the speed of the wave depends on that stiffness. So for instance, if I make it stiffer, if I make it a lot stiffer, it will be able to transfer the wave, it will travel much faster than if I make it kind of floppy, right? Now I've made it really floppy, basically. The spring is like an old, yeah, an old spring, right? It doesn't work well anymore, so it slows down. And also the density. Imagine if I make this much denser, you can
We can
kind of
make it
see
real
the
slow.
heaviness. You can see the heaviness of this now, right? If I may, it gets really slow. I think it just looks cool. Look at that. Yeah, so the denser you make it, the slower the wave, because now you can imagine there's more parts it has to go through, right? It has to go through more pieces, so it slows down. When you have
Well, the
fewer,
way I think of it is that each piece is less susceptible to acceleration. And so as a result, it accelerates slower than it otherwise would, and then therefore carries its influence to the next piece slower than it otherwise would.
mm,
Yeah, and here they accelerate quite quickly, and so the wave propagates through there.
yeah.
Let's see what happens if we make it really rare and super stiff.
Yeah, well, then it
Let's
will
do
go
it
real.
totally extreme. Okay,
Now it will
yeah,
be
so there we
fast,
go.
super fast, like
We
super
got
stiff, and
absolute.
yeah. So like we have to get the speed of light, so that means it has to be really stiff and not very dense, right?
Yeah,
So
yeah.
so this is this, right? So basically, the speed of a wave, of a transverse wave, is defined by that stiffness and the density. So the denser the slower, the stiffer the faster. And that's pretty much all we have to do to explain special relativity. So, of course, there's the objection again, well, it's constant for everyone, because now you can see it's constant on a global scale, right? If there's a medium with that stiffness and that density, what this sounds like what I'm saying, well, C is constant in an absolute sense, right? So obviously, well, how could we claim that every observer sees the same speed, right? And we'll explain that. And also the other objection, of course, well, now we just argued there's an absolute frame of reference, which is a preferred frame, which is like forbidden. So because we know we can't detect it, or we think we can't detect it, so we have to explain that as well. Now, again, just to be clear, in the previous episode, we talked about general relativity. And in that case, we were looking at, a twist. We were looking at a torsion and stretching and all that, which changed it changed the local speed of the wave because it was twisted and compressed and so on. Now, this time, we're not doing that, right? Here, we are looking at flat space. So we are looking for special relativity. We are looking at a region of space right now which is totally flat. There's nothing. It's the same inside and outside. There's nothing going on. Just to be clear about that. So to explain special relativity, we really just need to understand how clocks work. I think that's the main thing. And if you understand that, I think that's basically it almost. So what is a clock? And of course we have been saying that, oh, everything is wave, but let's maybe imagine it with a light clock first, because that might be the easiest. So we're building this clock where we're saying we have a little light emitter and a mirror up on top here, and then when the beam of light goes up and down, that's what we call one of our seconds, one of our whatever you want to call it. Just one click. That's one click. That's one of our light time or something like that. um, this is our clock, and we have no other clocks, right? We wear this on our wrist. That's what we have, basically. Um, and now what happens when this clock is moving? What happens? Because we know, as we have talked about before, the speed of light is a constant on the global, so on an absolute sense. In the absolute sense, this is shown by this grid here, right? This is like our medium, and the speed of light is always the same for this medium. And of course, we are watching this from the outside in a way. So now when we have a moving clock also, what happens is that moving clock, now, because the speed is constant in the absolute frame, right? This light clock here, it has to travel a longer path. So you can see that when we look at both of them together, when this takes for our outside seconds. So if I take my outside watch here and I count the seconds, this might be maybe 3 seconds. Now this one takes maybe 6 seconds. It takes much longer because it has a longer path. Because the speed of light is the same in this case in the absolute sense. So this clock ticks more slowly. There's another. Is that clear? Do you think that should be clear?
Yeah.
Yeah. Okay. Good.
Yeah. So the way I think of all of this is that the reason when I was young, I was always confused at why we thought about a light clock. Like, well, why not any other clock? And I'm not sure if special relativity has an answer to that, by the way, but
Mhm.
here's the reason we're talking about a light clock is we're choosing a clock to be some wave that goes back and forth, basically. A light
Yes.
wave. This blue
Hmm.
light wave is going back and forth. Um, and the reason we're choosing it that way is that we have reason to believe that any process of change inside of a medium is just a wave going back and forth. And
Yes.
time is nothing more than a measurement of change.
Yes.
And if
Exactly.
all
Hmm.
change is just the movement of a wave, then the light clock is sort of the quintessential clock. And we can
Yes.
see that when any object, any sort of, yeah, any structure moves through space, like, or rather moves through the ether in the way this pink clock is doing,
Hmm.
the waves have to go zigzag instead of back and forth. And
Yeah.
so it's going to take them longer.
Yes. Exactly. We can also do this in a circular clock. So same thing here. We just go travel
Oh,
around
that's
in a
cool.
circle. It just looks nice. I have fun with
Yeah.
simulations. I just like that stuff. As you can
So,
see.
and what I really like about this is that um, not all not all processes of change are going to be some kind of wave phenomena just going back and forth. Some of them are going to be wave phenomena going in a circle, like what you're
Exactly.
going to tell us about the electron. And it's
Yeah.
very
Yeah.
important
Yeah.
that the same kind of time dilation apply to a circular phenomena
Yeah. Any
as
kind of
applied
wave.
to a back
Yes.
and
Exactly. Hmm.
now. And have you mathematically confirmed that the circular phenomena are slowed by the Lorentz factor as well?
Yeah, yeah, we can show that. And there's also a paper by Robert Close I'm going to mention that he dives into the math in detail. I'm just going to show the sort of intuition and some math also, but I think it's the next slide. Let me see. Yeah, I do have a slide on that. So of course, another simulation. Sorry, I couldn't stop it. I just so here's the same thing again. Imagine this was the blue clock here, and here we have the pink clock. So, and now we are just adding basically drawing the triangle, the figure. I can't even pronounce the word. So, the length is the same for both. So the clock has length L here, this length here, and this one is the same because it's, nothing changes here. And if you look at the length, the time it takes for this clock, it's the length divided by c, speed of light. And now, when we look at this, let me just freeze it here. We can see that the moving clock, it took a longer path. Now, c is constant in the ether, in the global frame. So here again, the length of this is c times t. T is the time for this moving clock, okay? C times t. This length is still the same, and this distance is v times t. So now all we have to do is just, ct squared is L squared plus vt squared. Then we can factor out the c. So we get this, and then we can say the velocity that I have been using. So I was using a fraction of the speed of light. So like, for instance, here, zero 0.5 means half of the speed of light. That's beta. We can just to simplify a little bit, and then we can define gamma as 1 over this. We just resolve it, right? And then we see that this time t of the moving clock is nothing else but gamma times the time of the stationary clock. And you get exactly the Lorentz factor that way. So, I mean, it's pretty simple. It's really literally high school math.
Yeah.
You see that, right? Yeah. I think it's actually pretty simple. So that's all it is. The only thing we have to use here is that the speed of light is constant in the ether. Okay, so in that global frame, which we shall never speak of course. There, people always get upset when we say something like an absolute frame, but that's how you can derive it. Exactly. And there's actually also something called the Lorentz ether theory, which comes to the same conclusion. So, and it's known that this is actually compatible. So this is
And it's worth noting that I have a video where I show that a particular there is a special frame. There is a frame that um is the cause of duration dilation. And I show that in one of my earlier videos. Like I
oh, the
show that
rockets.
using a basic thought experiment.
I did the rocket too. I will show you. It's also one of the slides. Okay.
Cool. Yeah. So
So,
yeah, this is and another thing worth noting, like something people might object to is they'll say, well, you know, your speed of light in this simulation is c with respect to some special frame. And that's false. It's c with respect to any observer. Yeah, but
yeah, not
you're
yet. We haven't shown that
assuming,
yet,
yeah.
right? We haven't shown that yet. So far we've only shown, and of course, if I'm the outside observer, I can pick any frame I want. That's totally legal, like in special relativity. So
Mhm.
I can pick this frame where the stationary clock is really stationary. I can do that. I can pick the absolute frame if I want to. There's no reason I couldn't. But so far we have only shown that light slows down. Sorry, that the clock slows down. We haven't shown why it's the same for everyone, right? So far we haven't shown that yet. Because for this we also need length contraction. Like say
Okay.
if you want to go measure the speed of light, right?
So in other words, what you're saying is that like what we've shown here, you can presume that light is stationary with respect to any particular observer. That's what you're
Not
saying?
yet. So far, we've explained why a moving clock runs more slowly. That's what we've shown. And also, we have shown that we
Mhm.
can derive the gamma factor, the Lorentz factor, just through using the triangle, and we get the same. So far, it's compatible with special relativity.
I see what you're saying. What I'm saying is that a lot of people are going to object to what you've done so far
Mhm.
because they're going to say you're presuming this grid where light moves at c with respect to that grid. And that's not the way it works. Light
Oh,
moves at
yes.
c with respect to any given observer that you might choose.
Yes.
That's
And
what the
yes.
standard wisdom is. And
Mhm.
all I'm saying is I'm saying that is a convention. It hasn't been proven because we've never observed the one-way speed of light. That is a convention that yields results that work as part of special relativity. It is not the known fact of what is truly going on.
Yeah.
And so what Chantal is doing here is she's postulating a particular ether frame where c moves at where light moves at a constant speed with respect to that ether frame.
Yeah. And we'll
And we're
see.
going
Yeah.
to see that that yields the same results that we see in experiment.
Yes, exactly. Yes.
Okay.
Yes. Yes. So the next thing, yeah, to understand, the length contraction, we have to kind of understand the Doppler effect first. What does that mean? So, yeah, I think we all understand how the Doppler effect works for sound. And this is a bit fast, maybe. So let's just say we have an emitter that emits pulses. It could be sound or light, actually. It doesn't really matter. But for sound, people understand, how it works for sound waves, right? And we have a receiver that observes that pulse, that sound. But it's the same, actually, exactly the same formula for light as well. Um, and so far, nothing is exciting, right? So basically, we have, the source emits a pulse. There's no frequency shift of any kind. The detector receives the pulse, no frequency shift of any kind. So we just get, there's no shift basically right now. So now we start to move the source, for instance. And let me maybe increase the frequency a little bit so we can see that more clearly what happens. Or maybe this is too fast. Let's see.
There we go. That's good. It looks good to me.
So now what happens? Yeah, it's kind of fast. I wish I could slow it down a little bit. We can see now that the waves, because now the source is chasing the wavefront, right? Because again, the speed of the wave is absolute. So it's absolute in that medium, in air in this case, but it could also be in the ether. It's the same thing. And now we see the source is kind of chasing, the wavefront. And so these wavefronts are bunched up together. because of that, because the source keeps emitting pulses, but then next time the source emits a pulse, it's further along the way and further along the way. So this kind of pushes these wave fronts together. And now we can see what happens with the receiver. The receiver now sees these pulses bunched up together, right? You can see each time it highlights, when we compare to the rest, when it was at rest, the pulses were, I don't know what it was, 3 hertz or something. And now suddenly they're bunched up together, and you can see there's a shift now. So because of the source, it's moving, the frequency is shifted, and overall we see the observer sees something else now, right? The receiver. We can also do the other way. It's the same thing when we move the detector instead, right? So when we move the detector, we see the same effect, because now the detector is moving into the wave.
Mm-hmm.
So it will again see them bunched up, right? So the frequency will be shifted again, but on the detector side this time, right? So here we can see it's shifted on the detector side. Now we can also move both at the same. Let's see if I can manage to get them move at the same speed. And now when I look at it at the source frame. So basically now we see both of them are moving. And there's actually 2 shifts. So there's actually 2 shifts going on now. Let me just make it more extreme. Maybe we can see it. There is a Doppler effect here, but also there's 2 Doppler effects now. The source has a Doppler effect because it's the way it's emitting. And the receiver also is, they're not the same speed. It also has a Doppler effect, right? And so there's 2 shifts going on. And interestingly, when we look at the math, so we can do the math here. So basically there's a shift. There's 2 shifts going on. The source has a shift, and in this case, the receiver has a shift. And when we can just reformulate this, and we end up with a formula that makes it look, that's independent of the ether. So we can calculate this as if we only had a source and a receiver. We only need to look at the relative speed, which is nice.
Yeah.
So we can get rid of the air. Like when you calculate the Doppler shift of sound, you don't need the air, right? We can just use the relative velocity. And that's the same thing for light. It's the same thing. So there's 2 shifts going on. And yeah, and that's interesting also because if you look at the standard physics, right, who say there's no background, there's no ether, there's nothing, how do you even explain that? Like for light, how do you explain what's physically going on if there's no medium, right? Why would the source have a frequency shift if there's no ether? If it's not
Well, but
like, yeah.
but part of what they would say is that the relativistic Doppler formula does not look the same. It has a square root in it. Now, of course, the reason for this is because it is simply a combination of the regular Doppler formula with the duration altering formula. The frequency of the source is actually affected by the ether, in
Yes.
addition to the relative speed of the emitter and the observer creating a Doppler effect.
Yeah.
So that's the reason it's a different formula. And they won't be able to answer for you why there's a different formula.
I
They'll just say,
know.
oh, well, it's a different kind of Doppler effect that doesn't need a medium. That's
Yeah,
just what they'll
I
say.
asked this simple question years ago, and I got kind of attacked just for asking the questions. I'm like, why is there no? It's such a trivial question. Why couldn't they answer it? So that's also kind of what brought me onto this whole stuff. Like something's wrong if they can't answer the simple question. That kind of
Yeah.
bothered me. So,
Real quick for clarification for anyone who needs it, if you look at number 3, the beta formula, you notice the Doppler effect formula is written in terms of beta,
yeah.
where beta is V over C, and
Mhm.
V, correct me if I'm wrong, Chantel, V is the relative speed of the 2 observers, of the observer and the source, right?
Oh, yeah, sorry, I didn't say that. Yeah, exactly. Yeah, I didn't spell it
Yeah.
out. There are
So
2
this is
velocities. Like, let me have the source and the detector, but then overall V is the relative velocity. Yes.
Yeah, so I mean
Yeah.
the first 2 equations require an ether frame that you
Mhm.
posit an ether frame, which we don't know. We don't know the ether frame.
Yeah,
So
we
the
don't know
one
it. Yeah.
that's the one that's closer to what we can actually, or rather, the one we're actually allowed to write down is number 3, where we know the relative velocity of the source and observer.
The interesting thing is, even though you can use an ether, it cancels out. But it doesn't mean there is no ether. It just means you don't need it, you know. But it's not in violation of
It just
anything,
means we
you
don't
know.
know the frame and we don't need to
Yeah,
know the frame in
exactly.
order to account
Yes.
for the phenomena. Yeah, but
Yeah.
it's still just because you don't refer to the ether frame in this third equation doesn't mean that it's still the case that the third equation requires a frickin' ether frame. You're
Yeah.
positing an ether frame just by writing that third equation down, which is the point we've been making. To have
Yeah.
a Doppler effect, there needs to be motion through a medium.
Because yeah, otherwise you can't explain it. You ask someone, it's kind of fun when you see the answers. There's like, oh, you gotta draw a space-time diagram and like, oh my God, you know. But you know, anyway, we'll talk about maybe later also. It's just you get
Yeah.
crazy explanations, but it's really simple. Like the thing it makes it this is trivial. It's like high school math. Like, come on, any kid understands this, right? So okay, so how about length contraction? Now this I hope I can explain this. Because we haven't talked about waves matter yet, right? So let's imagine we have a rod here, okay? And that rod is just this is of course a simplification, but just like imagine this is a standing wave, just a simple standing wave. That's all we're doing. We and the rod, the length of the rod is so we'll be counting the notes here. So 1, 2, 3, 4, 5, whatever the number is. Now we can actually rewrite this standing wave as a traveling wave, a forward wave, and a backwards wave. When you add them up, okay, when you add these two waves up, you get a standing wave that looks like this.
Mm.
And
Hmm.
so all good is now right. But now what happens when we start to move this whole thing? So I'm now moving this rod, and you can see the little stars in the
Mm.
background.
Wow. Cool.
So now we have this. That's why I wanted to explain the Doppler effect first. Now the forward moving wave is squished the forward movement, and the backward one is elongated. And now when you add up those two waves, you get this, and then you can see how it gets squeezed more and more as you increase the velocity. So if matter is a standing wave, and if the you know if we count whatever the length that we you know the number of whatever the atoms or something that we use for counting the length, then you know basically what it means when you have a velocity here, it gets squished because the wave gets squished because when you add them up, you get this. Yeah, that's Robert Close will explain this in more
Wow.
detail. So he has a paper on this, but kind of makes sense, right? You can see how this works.
Yeah, this is fantastic, Chantel. So let me give my own. So this is one of my favorite graphics of yours so far, even though it's one of the simpler ones, but it's still because
Mhm.
okay, let me make sure I'm understanding. Let's go back to the situation where the blue and the pink are equal. Okay,
Yes.
great.
Hmm.
So here's my understanding. Correct me if I'm wrong. So we have reason to believe that matter is a wave. Okay, or I mean it. Yeah.
It's a
So
hypothesis
for
right now.
example,
We don't know. It's a hypothesis. We are, you know, yeah.
well, we know it has some kind of wave-like nature because of
Yes.
quantum phenomena.
Yeah.
We but
Exactly.
we
Yes.
but it could be a wave pushing a particle around. But one of the hypotheses we're entertaining is that it's just a wave,
Yes. Yes.
and that the particle aspect is caused by a particular way the waves interact with one another.
Hmm. Yeah.
So we're on this hypothesis that the matter is a wave in the medium. Okay,
Hmm.
and so let's take, for example, the electron waving around an atom.
Hmm.
Okay.
Hmm.
Now, your simple model for this is that it's a blue wave going forward and a red wave going backwards. So let's understand why we did that. Is because the electron is some kind of wave. It's really probably doing like a circular motion, but
Hmm.
one component of that is that it's going back and forth.
Yes.
Now, can we pause, Chantel? Can we hit pause on the
Oh,
blue and pink wave? Just
yes.
hit pause.
Yes.
Okay. Now, notice that as the blue wave goes forward, well, I'm a little unclear on this, Chantel, because don't we want the red wave to be equal and opposite to the phase of the blue wave because that would represent the red wave reflecting back? Like the backward wave is the reflection of the forward wave,
Oh,
right?
this is much simpler. It's just like any when you have a standing wave like this, you can
Mhm.
decompose it into a forward and backwards traveling wave. You can imagine that when you add them up, you get the
Uh,
same.
I see. Okay, so you're not necessarily trying to say that like I'm just thinking it this way. An electron is on some simple level a wave reflecting back and forth. It's really a 3D thing, but if we just look at one component, we can think of it as a wave reflecting back and forth.
Mhm.
That's why I wanted a proper reflection relationship between the
Oh,
blue
I
and the
see.
red
Yeah, yeah.
wave.
Hmm.
But that's probably not true. It's what you're saying. It's a standing wave, which is the yellow wave on the bottom.
Yes.
The
Hmm.
electron is this standing wave. It
Hmm.
is this constant oscillation of the medium that just sits there, and
Yeah.
that's what makes it an entity, is that it's this constant
Hmm.
phenomena.
Hmm.
Okay. And that wave can be decomposed into a blue and a red wave.
Yes.
Okay, now let's amp up the velocity. Let's give it a little velocity. So when there's a velocity, the Doppler shift makes the forward wave higher frequency,
Yes.
and the backward wave lower frequency
Hmm.
because we're
Hmm.
moving through the medium. This whole situate this wave is moving through the medium to the right,
Yes.
which once
Hmm.
again the blue wave gets higher frequency
Hmm.
because it's going into the ether.
Yes. Yes.
Yeah, and then the red wave is going away from the ether, so it's receding from the ether, so it gets a longer wave. And this adds up to the yellow wave down there, and the resulting. And if we look at the peaks and or not the peaks and troughs, but the nodes of the resulting waves,
Yes.
which is represented by the white dots, the nodes get closer together
Yes.
the
Exactly.
faster you go.
Yeah.
So let's look at it normal first so that the audience can just look at that. Look at it no speed. So you have your dots basically to the left of each node. Um, but then when we increase the velocity, the waves interact in such a way that the nodes get closer together.
Yes.
And that accounts for the wave overall shrinking, which is the freaking length contraction of matter.
Yes. Right. Yeah.
Yeah.
So, of course, let's see. Now, of course, the question is why is the length contraction the same gamma factor that we have for time dilation? Because see, once we have those two things, if the that's the whole question about the Michelson Morley. Why is this conspiracy, right? That we have
Yeah.
the slowdown, is the same as the length contraction. It sounds like it's made up, like some kind of
Yeah.
conspiracy.
Yep.
So, yeah, this is the same thing again. As you can see, it's the same thing again. I'm just now, what I'm doing, writing out what exactly happens. That's why we looked at the Doppler effect before. So we have the forward Doppler effect. And this is what I was writing out before. Remember when we had Doppler effect here? And
Hmm.
we can we can use gamma. We can, the formula for gamma, we can put that in here like this. You can rewrite it. So overall, this is gamma times 1 over plus beta. And then for the backward wave, let me just scroll down. I think because I have the numbers down here also. Um, the same for the backward wave, right? Here's plus beta, there's minus beta. And now the matter structure is the average, basically. So going the forward plus the backward divided by 2. And when we do that, we get gamma. We get the same gamma factor, basically. Um, so this is no conspiracy. It comes out of the Doppler effect ultimately, and which, of course, is a result of the speed of light being constant in the ether frame. So the conspiracy is just because it's the same origin. It's basically the same. It's the same. It's because
Yeah.
of,
And let's think about this for a moment. In a Michelson Morley experiment, you're comparing a wave that goes a light wave that goes upstream and then downstream. You're
yes,
comparing that against a wave that goes across the stream and then back.
yes,
Okay.
hmm,
The across the stream and back, that's a light clock.
yes,
So that's your standard you're measuring the upstream downstream
hmm,
against,
hmm,
right?
yeah, yeah,
And your
exactly.
standard is changing in the exact same way that your clocks are changing.
Yeah, exactly.
Okay. Meanwhile, the light that you're trying to measure, the upstream and downstream light, that light it has the same basic structure as the matter That's part of your table.
Yes,
Because the matter as part of your table is basically a wave going back and forth, so it shrinks by the same amount. So your standard of
exactly.
time changes
Mm.
that you're measuring the back and forth with, and your standard of length changes. And both of them can change in such a way. And so as a result, these cancel and you get the exact same speed of light.
Yeah, it's kind of frustrating, right? Because yeah, because it seems like a conspiracy. So, yeah, here I have another one.
It did definitely seem like a conspiracy to me, but then we realized we're using the Michelson Morley experiment was an attempt to use waves
Oh, I have it
to
here also. Yeah, I can actually run.
okay,
Actually,
I won't steal your thunder.
no, 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 it's good. No, I have. I wanted to show because also there was a bug. Like someone complained that I wasn't contracting this side, which is there was a bug. So we have to with length contraction. Of course, we have to contract the whole apparatus, of course. So now
Oh
that's
yeah,
fixed.
yeah.
I ignored the left side. Even I'm now also
Well, but the left
contracting.
side doesn't matter.
Yes,
The left
still, but
side, that's
it's
just,
confusing. So
yeah,
now
I mean,
it's
but it's true. Yeah, we need to contract the whole thing. There's no question. Yeah.
so
It just
anyway,
so
that's
happens it
yeah,
doesn't affect the result. Yeah.
yeah, yeah.
I didn't catch that last time. Yeah, yeah. I remember it didn't contract on that side. Yeah. So the upstream beam is shortening, and the cross stream beam is taking longer because it has to go diagonally. And so it cancels to the same effect.
Yeah.
And it cancels to get the exact same it cancels in such a way as to make it so that there is no difference in phase when they both reach
Yes.
the
They
detector.
if these two balls here, if you look at they end up here at the center together. So because of that, because the length contraction is same, shortened by the same amount, it's yeah, they still end up together. And of course,
Yeah.
in the original experiment, they didn't consider that, right? They assumed there's no length contraction. They didn't consider that. So that's why, of course, if you assume there is no length contraction, well, yeah, see, they're not going to end up here together. Yeah, then you would expect the phase shift, right? If you're not considering length, if you're just assuming it doesn't affect the apparatus, then you have a problem because you're expecting a phase shift, but there wasn't any. So a lot of
Yeah.
people don't know that, unfortunately. Yeah.
Yeah.
Here, and you know what's funny? You know what the definition is of a meter? It's like unbelievable. If you look it up, if you just Google what's the definition of a meter, it's the length of the path traveled by light in vacuum during a time interval of 1 over c.
Yeah.
That's pretty crazy. It's like, come on, this is like,
I really, yeah, I have to really think about to me, this has actually been on my mind for a while. It seems like we don't fully understand the repercussions of this choice. It seems like this choice would cancel certain phenomena, which would otherwise perhaps be measurable. Maybe that's not the case. Someone probably would have figured that out by now
yeah,
if
yeah.
that's the case. But
It
it
sounds like
seems
it's
like it's going
cheating.
to
Yeah,
sweep
yeah, yeah.
certain phenomena under the rug.
I mean, yeah, basically it sounds like, well, that's just a weird definition, right? It sounds like, come on, if you define the length in terms of speed of flight, of course you're going to allocate length contraction, but it's just fake because it's definition. Now we have been showing, well, now it's not only it is a weird definition, but it happens to be correct because matter is composed of waves, and so that's why we saw the length contraction. It does end up that way. It's just weird that it's the meters actually defined that way. I mean, it makes sense overall, but when you first see that, it's like if you want to show the length contraction, but using this definition of a meter, well, that's kind of circular, right? So
Yeah, I mean, I'd have to think about this a lot because it seems like there's big repercussions. It might actually even be a good thing that they've defined it this way, but I'd have to think about it.
yeah.
Um,
It's just funny. Like
yeah,
I showed length contraction a different way. So I wasn't using this. I could have used this definition. That's just the definition. That's it. But that's not really an explanation, right? That's just the definition. So when we have to explain it using the Doppler effect, then it's much clearer because we count the nodes and they get, in the ether frame, they get contracted. It does end up that way, but that's not an explanation, right? That's just a definition. So, and here is a more like interesting simulation, maybe in a spiral in Let's see, I hope my computer can handle it because so here's just a spiral wave. There's nothing it's just a spiral wave. And what I'm doing now, I'm now moving it, relative to the ether, and you can see you get this kind of contraction, this whole thing. So yeah, you get this kind of double effect. It just looks kind of interesting because it's a circular wave. You can see how the envelope of this wave, like the whole envelope, I guess, contracts, right? It gets flat.
Yeah. It gets really messed up at this point.
Yeah.
Now, and the reason you've drawn it this way is that you have reason to believe that matter consists of some kind, one of these waves in the elastic solid, which goes in a circle. That's why you've drawn
I
it in
just,
this
yeah, I just
spiral.
wanted to say with that it's true for any, it doesn't matter what the wave looks like because right
Oh,
now we've only looked at nice waves going up and down and sideways. It's for any wave, right? It is whatever the shape is of the wave packet, you will see the same kind of contraction, right? It doesn't matter what that wave looks like exactly. This is
yeah.
basically, yeah. Um, so another thing is, oh, by the way, so this has been inspired by Robert Close. He has, and I'll also add the links. He has also done some simulations, and I've been inspired by Robert Close a lot. I also wanted to talk briefly about how we measure length. So now hopefully this should be trivial almost. So on the top is again, just look at the top first. It's just two subs, the stationary clock basically and the moving clock, right? Same thing. We understand how this works now. So this one does, when it goes one click, this one takes much longer, right? And it's contracted by the gamma factor also. Now let's say we want to measure the length of the ship. Do they notice? The question is, does B notice that their ship has gotten shorter, right? You might say, well, wouldn't they notice? And how they measure it? Well, they send a beam of sonar along the ship and back, and you can see it goes forward and it gets reflected backwards. And so the length of their ship that they measure is, c times the time interval divided by 2, and that's one of their sonar meters. It's just, so their ship has the length of one sonar meter. And now this contracted moving ship does the same thing. They send a beam of sonar and it gets reflected. And you get, even though it's for us outsiders, we have our own, global clocks. We can see they took longer, but, they wouldn't notice. For them, it's just one tick of their sonar clock and they measure exactly the same length. They measure one sonar meter because, again, speed of light, the time difference divided by 2, and you get the same result. So that means they couldn't detect that their ship got shorter because same thing, length contraction and the time dilation, basically.
Mhm. And it's worth noting that the speed of light, which is allegedly the one way, which is allegedly that. So yeah, let me start over. It's worth noting that the speed of light, which is allegedly the same in all reference frames, the one-way speed of light,
Mhm.
is the standard of what we take to be a meter. So definitionally,
Yeah.
the object would never like it's even sort of true if you take that definition of a meter. It's
Mhm.
true that the object literally doesn't change. Well, not literally, but it's true that the object does not change in its length in meters because the definition of the meter itself actually changes as you
That's
as
funny.
you
Yeah, yeah,
move to
yeah.
a different frame.
But even if that were wrong, like even like if someone claims, well, that the definition is wrong, we would notice, like, why did my stick get shorter, right? We wouldn't notice. The point is, even then, we wouldn't notice. No matter what we do, we
Yeah,
wouldn't notice.
right.
Unfortunately, we
Because
couldn't
any
notice.
standard that you use, any standard we're currently aware of by which you would measure the length, that standard itself is made of waves and therefore gets changed by the ether in the same way the object being measured is changed
Yeah,
by the ether.
exactly. So what comes up a lot, of course, is the twin paradox. So the question now is this actually a paradox? And can we use it to detect the ether, maybe? So the situation is, let me just no speed at all initially. So we have two twins, one stationary, and they removed any Earth or sun, so there's no gravitational field at all. The one stays at home, the other one flies off to some place and then comes back. And as you can see, when we use the ether, there's really no paradox because we can measure everything relative to the ether, right? We can clearly see, we can calculate the gamma factors and everything. And we can see clearly that the moving twin aged less because the time on the moving ship was slower, basically, right? So when they come back and they meet again each other, then the one that was stationary, and we can see, let's see, I think it calculates the time difference. Basically one of them is older than the other one. The one that's moving ages less. Even when we have now we're moving this whole situation, so now we are actually moving this whole thing in space. So, oh, the ether wind. Oh, sorry, I wasn't actually doing the ether wind. Okay, the ether wind. I mean, we're now moving the whole situation relative to the ether. Let me just do that. So now, okay, now we have the same situation again, and we are doing the same thing in. And it doesn't. The point here is it doesn't even matter how, if you're moving this whole scenario, or if it's stationary, or if it's going the other way, you will always get the same result because of the gamma factor and all that. But still, the one that moves more, ages less overall. So it's actually very simple to explain, right? There's no weirdness. It's kind of obvious. Well, if moving clocks run more slowly, yeah, I mean, the one that moves more ages less. You know what I mean?
Well, hang on. That's not quite the way to say it because someone could say, well, does twin B move more than twin A? It depends on what you mean because on the right in this video in this simulation during the rightward journey twin B moves less, but
Yes,
during the leftward journey it moves more because it's moving along with the ether at
yes,
first, then it's moving
yes.
against the ether. So the way I think of it is the object that changes its motion with respect to the ether ends up undergoing less change.
Yes, because overall, you're right. So if it goes on one side, it will actually almost be, it could be stationary even, right? Even though it looks like it's moving, but it's actually stationary. But overall, because it has to go back and forth, overall, when you calculate the average, when you calculate the total movement, the one that moved more relative to the ether has aged less, basically.
Well, again, it's hard to say which one moved more relative to the ether.
Mm.
Oh, wait, I see. I see. Did it? It's definitely true that the one that changed its velocity with respect to the ether, that's definitely the one that aged less. But is it true that overall B ended up moving more with respect to the ether overall?
Yeah, it doesn't even matter which way we go. Like we could move it the ether the other way. It doesn't
Hmm.
even matter. It's always the same. You get always the same result also. And it's interesting. It's just
Yeah.
all the gamma factor. You get the same thing. It's interesting. So it doesn't even matter. So that's also why you can't use that experiment to detect an ether because it doesn't matter. You always get the same result no matter what you do. No
Yeah.
matter what you do.
Yeah, it's still true that whichever ship changed its velocity with respect to the ether ended up having less duration or less change or less time, if you will. Even though that's true, you can't tell what the ether frame is because it
Yes.
doesn't matter what the ether frame is, you get the same result, the
Yeah.
same
Yeah.
difference between A and
Exactly.
B.
Unfortunately.
Yeah,
So now,
yeah.
of course, we can think, hey, we are smart people, right? We can figure this out. We can figure out a way to detect the ether. We want to detect the ether. And I've gotten emails also, so I wrote this simulation. Aberration is such a thing, right? Because when you talk about this, a lot of people will say, hey, wait a minute. If I have this thing here, so I have just a light beam and a detector. Now, when I start to move this, right? When I start to move this, wouldn't we get like a shift, like the detection plate that would change the location? You know what I mean? Because we're moving away. So we are emitting this light, the
Hmm.
whole apparatus is
Yeah.
moving. Wouldn't there be like a change in the place where we are detecting this, like the aberration?
Hmm.
And actually, no, we don't, because you can see the light. Yeah, the light goes diagonal, but it's not like we are sending off shooting. I don't know. It's just it's a particle or something, right? It's a light wave, and
Hmm.
it doesn't matter how you move it, it will always end up in the same place, unfortunately. So again, that's again something we can't use. We can't use it to detect any ether,
Hmm. I'm
unfortunately.
not fully couldn't someone make the following argument that the light that hit the detector, the light that hit the detector would let's see, it's coming in at an angle now.
Yes.
So as a result, wouldn't the luminosity decrease because it's coming in at an angle?
Maybe, but everything is compressed the same way. Like everything is gamma. The gamma
Yeah.
factor is everywhere. Gamma factor is compressing your apparatus. It's slowing your clock. It's always the same gamma factor that comes into play,
Yeah.
unfortunately. So it all cancels out. And then all these ideas
Oh
people
boy.
have to be clever, it's unfortunately, I mean, maybe I'm missing one because, I myself have gone through all these and thought, hey, I have a clever idea, but then it didn't work. So now I'm pretty
Yeah.
sure there's just no way that we can detect it, unfortunately. And people, again, these links are all free. You can play with this. You can change the code. There's also some explanations in there. So another problem is what people sometimes forget is clock synchronization, the issue. So I have this thing here because people always come up with experiments where we have to move a clock. The problem is, as you know, right? So now we have three clocks. They're all in sync. This is our reference clock here. The thing is, as soon as you move a clock, let's say moving this just a little bit, you can see now the light path is longer, right? It slowed down
Hmm.
already. It's, it's just so unfair. Yeah, yeah,
So now it's behind because it had to move additional distance through the
yeah,
ether. The clock is now behind, basically.
yeah,
The
exactly.
total quantity of change, that is, of bouncing back and forth, the total quantity of change is now less. And yeah, we can see, I see, you've written in red how much time each clock has lost
Yes,
as it moves.
exactly. Yeah.
That's this one's really cool too. I really like this
It's
one.
nice. It's kind of cool. You can just
Yeah.
drag stuff around. You can see
And yeah,
literally
you can
how it's
watch that
slowing
extra
down.
distance actually occur with this green path or the pink path.
Yeah, yeah,
And
yeah.
that's a bunch of extra distance that the blue light didn't have to travel. And so the
Exactly.
blue
Yeah.
light continues to show a longer amount of time because it underwent more change than the blue and the pink clock
Yeah,
because the blue and the pink
exactly.
clock can't do as many back and forth motions because they got longer to go.
Yeah, exactly. And I think playing with this helps also to just understand the ideas. I mean, that's for me. It helps me understand when I have a question. I just like to play with stuff so I can understand it better and get a better like intuitive feeling also for this because to me it just makes more sense when I can see it.
Yeah,
Yeah.
and we'll include the links. Chantel will include all the links to
Yeah, yeah,
these
yeah.
simulations.
I'll send you the links. Exactly. Um, Now, of course, we think we are super smart, right? We can figure out a way that doesn't require clock synchronization. Here's another experiment we can do. So you and I, right? We are both in a rocket. Let me just run it. So let's just look on the left side here. This one is stationary in the ether, okay? This red one, that's me. Let's say that's me, and then you are in the rocket. Now we know we can't synchronize clocks, so we're not even going to try that. And it's kind of a similar thing that your rocket example, even simpler. So what we're doing is we agree that when you fly past me, okay, you start to send out 5 pulses. That's all you do, 5 pulses. Because when you fly past me, we can synchronize we see each other right there, and you start your 5 pulses, and I just measure how long it takes for them to receive. So one, 1, 2, 3, 4, 5. So it took, 12.1 of my own seconds, of my red seconds here, to detect your 5 pulses, right?
Okay.
So now we think, obviously, if you look at the other situation on the right side now, we should be able to see a difference, right? The clocks, they should show a different time because now I mean, clearly you are the one moving, and so your clock is running more slowly. So we should be able to detect that. That's what we think. And when we do that, unfortunately, as you can imagine, even though you can see it takes a lot longer. So now you're detecting the tick. So I'm now sending out as you pass me, I'm sending
Mhm.
out five pulses. You just record how long it takes you to see those five pulses. Now the thing is, even though for us like outside viewers, we can see, oh my God, this takes forever. Well, your clock slowed down, right? Your clock slowed down. So it takes you also 12.1.
Yeah. So the B clock is going slow because it's moving through the ether.
Yes.
We're
Mhm.
seeing all of this from the ether perspective, incidentally. So we're sort of the clock we're using, looking at this either situation is from an ether perspective.
Yeah.
Um, and so because B is moving through the ether, its clock runs slower. And even though the light waves take longer to reach it, it still measures the same amount of time between pulses.
It's funny. It's funny because I wrote this originally because I wanted to show that we can detect the difference. I was kind of naive.
Oh,
I thought, hey, I have this idea, no clock synchronization. Oh my God, I figured out a way, right?
uh-huh.
So I'm like, and then I end up with the same, like, how could that be? And of course, it's the same thing. It's always the same gamma factor. So
Yeah,
yeah, it's fun. It's frustrating. And
it's
then
not
people,
fair.
it's not fair. So I'm convinced now. I don't know if there's any other but at least these ways are not but this is not possible to measure detect the ether. So everyone who claims, well, if there's the frame of reference, we can detect it. No, you can't. There's no way. And the funny thing is, you brought up this rocket experiment, right, in your video. I was trying to do something similar with this, and the funny thing is that, basically what you were doing, so you have, A and B, just like before, they synchronize their clocks, and A starts counting the time. And then when wait a minute, I can slow down the simulation speed a little bit. So yeah, otherwise it's too fast. So as A passes C, then C starts to continue counting. So A sends the time it has measured so far, gives it to C. It. That's totally fine because they're just passing each other, right? That's fine. And then we will see what the difference is for B. So, and we can run the simulation three different ways. So here I picked B stationary, and we can see the time difference overall is like 0.05 seconds in this case, zero point zero 0.05 seconds. And now, again, we think we can now use this to detect where the ether is or something, because B is stationary in this case, right? So B's clock runs faster. Now let's try the same thing, but we pick A stationary. So I'm using the same relative velocities, all the same situation. It's just A is now stationary. And we do the same game again. So when it starts, A starts to count. And when A sees C, it passes on the time to C. So the clock A starts, and now it's giving it to C. And then we have to wait until C catches up with B. And then we compare the time. And are you surprised when I say the time difference is exactly the same?
Yep.
So unfortunately, again, and even with C stationary, now C stationary clearly, but still you get the same difference. And the reason is, of course, well, one intuitive reason is that, the overall there's a different movement. So, the rockets B and C, they're moving, or whatever, the movements is not the same. One has to travel a lot faster to catch up in each situation. And that's why overall you can explain that. I think that you end up the same way intuitively. It's a little bit harder to explain, but when you do the math and you do the calculations, so I've written down all the gamma factors and everything, you get exactly the same result, unfortunately.
Yeah. So the lesson here is that we cannot use this version of the twin paradox to measure the rest frame of the ether.
Yes, we cannot.
However, what I would add is that I have a video where I examine this version of the twin paradox,
Mhm.
and you can see that video in the description.
Yes, yeah, you should
This
put a link
version of
there.
the twin
Yes.
paradox, if you reason from it properly, actually shows that there is a special frame, or very
It
likely
makes
an
sense.
ether frame.
Yeah, it makes sense
Because
because there's
basically
something that
these,
affects the speed, right? Obviously, there's something there that affects the speed of these clocks. So,
Yes.
I mean, logically it makes sense. There's no, a kind of no-brainer in a way. It's just a pity that we can't
You'd be
use it to find
surprised.
out.
I've
Yeah.
I've gotten into long debates with people who don't get it.
Okay.
I don't know. I do think it's a no-brainer, but once you see it, but getting the pieces in place to see it is the hard part. I'll
It's
just
really
re
hard. Yeah,
so
yeah, yeah. It's
yeah,
really hard.
you can watch the video, which I've linked in the description. I'll give a quick version of the argument here. Um, the time elapsed on A plus C. Remember, we're adding clocks A and C in this. Oh,
Yes.
go back so we can. Remember, we're adding clocks A and C, and we're comparing it to the green B clock.
Yes, exactly.
The
Yep.
clocks
Hmm.
on A plus C
Hmm.
show less time than the clock on B. Okay?
Yes, exactly.
The
Hmm.
only thing that could have caused that difference is their difference in speed.
Yes, yes.
Or their difference in velocity, because that's the only difference. It's their
Makes
difference in
sense. Yep.
velocity. That's the only thing that could have caused the difference on the clocks. A difference in velocity is always a difference in velocity with respect to something. What
Right.
is the speed of that something? I don't know, but a difference in speed with respect to that something is the cause of the difference in the clocks.
Yeah, makes sense. Yeah, yeah, I get your
So
argument. Yeah.
that's how we know there is a something here. There
Yeah,
is a
it makes sense.
something that's
Yeah, yeah.
causing the clocks to
Mm.
and further, and I'll give the further argument that shows up in a different video. All action is local. So
Yes,
the
yes.
thing that's causing the difference in the clock must be an entity that is at the location of the clock itself. So it's like it's at the
Yeah.
location of the
Hmm.
A clock as A moves along, or the location of the C clock as C moves along. So what's causing the difference? It's some entity at each location of the clock as it moves. Well, what do we call that? It's an entity at each location. It's like filling, it's everywhere. That's an ether. It's this
Yeah, yeah,
entity everywhere.
exactly.
And when you
Yeah.
move through it, it changes the speed of the clock. And you've given us a fantastic hypothesis as to why that might be the case. It's
Mm.
because of the slowing of the wave speed as it goes back and forth
Yeah.
inside the inner workings of those
Yes,
clocks.
yes, exactly. So, and of course now we you brought this up also. Hey, we're clever. We can do but especially the one-way speed of light. Surely we can figure this out, right? I was hopeful for a long time too, but now the problem is, so of course we think we are smart, right? So we have two clocks. Let me just maybe run it stationary and then just kind of slow right now. I hope I can slow. So we're moving some clock over, and of course we're not stupid, right? We know there will be the time will be affected of that clock. We know we can count. We know special relativity, so we can calculate, well, how much slower will that clock run when we move it from A to B with a certain velocity, right? We move it at 0.07 C over here. We know how long it took. We know length contraction, right? So we're doing so we can calculate, where the clock so that the clock will be synchronizing because we know the distance, we know length contraction, we know all of that. We can do the math, right? See what I mean? So we calculate there is going to be an error of 7 nanoseconds because we moved the clock. Remember, because the moving clock slows down, but we know that, right? So we're calculating, well, it's got to be 7 nanoseconds that we have to fix once the clock is there and be on this end, we have to change the time a little bit we have to change it by 7 nanoseconds, right? To make it right.
Mm-hmm.
Okay.
Mm-hmm.
I know this is brutal. So now, of course, yeah, yeah. And of course, forward speed here is all stationary. Backward speed, 300,000 kilometers. Forward plus backward divided by 2, 300,000 kilometers. Now we're adding this ether wind. So we are now moving this whole apparatus, right? And we're doing the same thing again. Again, the problem is now, and of course, the speed this way will be slower. Like it will take a lot longer. And like with the Michelson Morley, it will be faster backwards. But the problem is, we only fix the time dilation considering the relative velocity between those two, not the overall velocity. So when you do the math, so we did correct again. We corrected. We thought we have to fix 7 nanoseconds, right? That's how much we changed clock B. Because we don't know how fast we're moving relative to the ether. We just know relative to each other how we were moving. So we're fixing that delay. That's 7 nanoseconds. But then when you do the math, it still ends up as you still measure the same, unfortunately. Now, of course, you can check that because I did this mostly today, so maybe there's an error. I hope. I hope it's wrong, and I hope we can measure it. But when I ran it, it seems like again the conspiracy. But you feel free to try. So, but it looks like even then, even measuring the one-way speed we will just not be able to see it. Even though there is, like as outside observers, we can see clearly. It takes a lot longer from as an outside observer, we can see it. But when you measure it with those clocks and all that stuff, then it just won't work. So I do want to bring up Robert Close. He has done also several simulations. I'll put the link in the description also. And he has written this paper, and here's this paper. And he has written actually a lot of stuff. He has written books and many scientific, publications. One of them is the other meaning of special relativity. If someone wants to get more into the math, really, and everything, so yeah, I would recommend for people to read that paper. So interesting overall, when we look at this whole thing, it seems to me that, special relativity is not fundamental, but it's really emergent. So what I would think is that you would, if there was some kind of fish made out of sound waves, you know,
Uh-huh.
and they use sonar, right? And their sonar measuring sticks, they would also come up with special relativity exactly the way we do. So it's
Yep.
just a phenomenon of any pure wave system has special relativity. If you had creatures in a phonon, this is from Grok here, so I don't know. This is
Hmm.
just, I like to play with that. So if you had like phonon creatures in a phonon in a crystal using, they have phonon clocks and phonon measuring sticks. Well, same thing, right? It's a wave system. If everything is made of waves in any system, then you end up with special relativity, basically. So yeah, and that's so in summary, basically, then that's what I was just basically summarizing. But in standard special relativity, basically this constancy of speed of light is postulated. It's not explained. There's no mechanism explained. The Lorentz symmetry is fundamental again, and there's no frame at all. What we are saying, or what I'm saying, that there is an elastic continuum of some sort, that the wave speed is determined by the stiffness and density of that medium, that all local, now of course the speed of light is constant in that medium, but still because of length contraction and time dilation, all observers locally see exactly the same speed of light, unfortunately. It's emergent, and so far at least so there is an absolute frame, but so far it has not been possible to detect it. And I put an asterisk there because maybe in the future we'll find a way, because I don't know, maybe there's some way, if that medium does have a smaller structure, for instance, as an example, let's say Planck length, let's say there's little, some kind of crystal made of Planck particles, who knows, something. If what we would expect from a normal medium, once you have a light wave with the wavelength that approaches sort of that length, that Planck length, you would expect the speed of light no longer necessarily to be constant, and it might be slower, right? In a normal material, that's what you see when you have a wave in some material, and then the wavelength is similar in order of magnitude to the grid structure, the structure of the material. The wave slows down a little bit. So if that's the case, we should be able to, in the future, maybe see some slight delay, of some gamma rays, for instance. Who knows? I don't know. That's just a hypothesis. Something. If that's the case, we might be able to do something in the future. I don't know, but that's really the only way I see at the moment.
Wow. That would really be something.
Right? Yeah, yeah. Something to think about, right? Because if we do have
Yes.
this hypothesis, we should think about, is there other things we can do, other experiments, and so on. Um, yeah, so this concludes the episode on special relativity. So next episode, we'll talk more about, well, why do we think everything is made out of waves, right? Because clearly people think they're photons. I mean, Einstein got his Nobel Prize for that. So maybe we need to talk about that, right? How can we justify the idea that maybe everything is made of wave? Is there any reason for that? So that will be the next episode.
Fantastic. Well, this has been a lot of really good visualizations, and I really hope it explains a lot for people who have been wondering what lies behind these phenomena. What is the cause of these
Mm.
phenomena? And now we have a very excellent visualizable hypothesis for that. So thank you.
Thank you.